Matter, which has mass and occupies space, exists in three forms: solid, liquid, and gas. Solids like bone, liquids like blood, and gases like oxygen are examples. Atoms, the smallest particles with chemical properties, form elements. There are 92 naturally occurring elements, organized in the periodic table. The periodic table of elements organizes the 92 naturally occurring elements that make up matter. Each element is represented by a unique symbol and is arranged based on atomic number, electron configuration, and recurring chemical properties. This systematic arrangement helps in understanding the relationships and properties of different elements. The human body is primarily composed of a few key elements. These elements are crucial for various biological functions and maintaining overall health. Understanding their roles helps in comprehending human physiology better. Atoms consist of three subatomic particles: neutrons, protons, and electrons. Neutrons have no charge and a mass of 1 atomic mass unit. Protons, also with a mass of 1 atomic mass unit, carry a positive charge. Both reside in the nucleus. Electrons, negatively charged, are much lighter and orbit the nucleus in electron orbitals. Elements are represented on the periodic table by unique chemical symbols, often the first letter or two of their name, like C for carbon. The atomic number, indicating the number of protons, is above the symbol. Elements are arranged by atomic number, and the average atomic mass, the sum of protons and neutrons, is below the symbol. To determine subatomic particles, the proton number equals the atomic number. Neutrons are calculated by subtracting the atomic number from the atomic mass. For instance, sodium has 12 neutrons. Electrons match the proton count. Atoms have electron shells surrounding the nucleus, each with specific energy levels. The innermost shell holds 2 electrons, while the second can hold up to 8. Shells closer to the nucleus must be filled first, ensuring stability in atomic structure. This slide presents the general atomic structure. Please refer to Figure 2.2 for a visual representation. Access the text alternative for detailed descriptions of the slide images. Isotopes are atoms of the same element with identical chemical characteristics, but different atomic masses due to varying neutron numbers. For instance, carbon has 3 isotopes: carbon-12 with 6 neutrons, carbon-13 with 7 neutrons, and carbon-14 with 8 neutrons. Carbon-12 is the most prevalent. The average atomic mass is a weighted average of all isotopes. Radioisotopes with excess neutrons are unstable and release radiation as they decay. This radiation includes alpha particles, beta particles, and gamma rays. The physical half-life is the time it takes for 50% of a radioisotope to stabilize, ranging from hours to millennia. The biological half-life refers to the time needed for half of a radioactive or non-radioactive substance, like hormones or drugs, to be eliminated from the body. Medical imaging of the thyroid gland utilizes iodine radioisotopes. These radioisotopes, introduced during procedures, mimic non-radioisotopes in cellular processes. Scintigraphy, an imaging technique, highlights areas of the thyroid with reduced radioactive iodine uptake, aiding in nodule detection. The periodic table organizes elements by valence electrons. Column IA includes hydrogen, lithium, sodium, and potassium, each with 1 valence electron. Each subsequent column adds an electron. Column 7A elements have full valence shells, leading to chemical stability. Helium and neon are examples of inert noble gases. Elements strive for complete outer shells with 8 electrons, following the octet rule. This drive leads them to lose, gain, or share electrons. Noble gases in column 8A already have full outer shells, making them stable and unreactive. The periodic table is organized based on valence shell electrons. This arrangement helps predict element behavior and reactivity. Refer to Figure 2.4 for a visual representation. Chemical compounds are stable associations of elements in a fixed ratio, classified as ionic or molecular. Ionic compounds consist of ions held together in a lattice by ionic bonds. Ions are atoms with a positive charge, known as cations, or a negative charge, known as anions. They form through the loss or gain of electrons and have significant physiological roles. For instance, potassium ions are used in sports drinks to replenish those lost in sweat, and in large doses for lethal injections. Sodium forms a cation by losing an electron, achieving stability and satisfying the octet rule. This results in sodium having 11 protons and 10 electrons, giving it a +1 charge. Chlorine becomes stable by gaining an electron, forming an anion with a charge of -1, satisfying the octet rule. It now has 17 protons and 18 electrons. Additionally, polyatomic ions, like bicarbonate and phosphate ions, consist of multiple atoms. Ionic bonds form when cations and anions are bound by electrostatic attraction, creating salts like table salt, sodium chloride. Sodium loses an electron to chlorine, forming a lattice crystal structure. Similarly, in magnesium chloride, each magnesium atom loses an electron to 2 chlorine atoms, resulting in an ionic compound. The formation of an ionic bond between sodium and chloride involves the transfer of an electron from sodium to chloride. This results in the creation of positively charged sodium ions and negatively charged chloride ions, which are held together by electrostatic attraction, forming a stable ionic compound. Covalent bonding involves the sharing of electrons between atoms of different elements, forming covalently bonded molecules. These are known as molecular compounds, such as carbon dioxide, CO2. However, molecular oxygen, O2, is not considered a molecular compound, as it consists of the same element. Chemical formulas are crucial in chemistry. The molecular formula shows the number and type of atoms, like H2CO3 for carbonic acid. The structural formula reveals the arrangement of atoms, such as O equals Cc equals O for carbon dioxide. This helps differentiate isomers, which have the same elements but different spatial arrangements. Glucose, galactose, and fructose share the same molecular formula, C6H12O6. However, their atoms are arranged differently, making them isomers with distinct chemical properties. In glucose and galactose, carbon atoms are numbered consecutively, starting from the carbon next to the oxygen in the ring, while in fructose, carbon 1 is attached to the ring. Covalent bonds involve atoms sharing electrons, typically when both need electrons. In the human body, these bonds commonly form with hydrogen, oxygen, nitrogen, and carbon. This sharing stabilizes the atoms, allowing them to achieve full outer electron shells. The number of covalent bonds an atom can form varies. Hydrogen forms the simplest bond by sharing its single electron. Oxygen requires 2 electrons, forming 2 bonds. Nitrogen forms 3 bonds, while carbon can form 4 bonds, allowing for diverse molecular structures. A single covalent bond involves 1 pair of electrons shared, as seen between two hydrogen atoms. A double covalent bond shares two pairs of electrons, exemplified by two oxygen atoms. A triple covalent bond involves three pairs of electrons shared, such as between two nitrogen atoms. This slide focuses on single, double, and triple covalent bonds. These bonds involve the sharing of one, two, or three pairs of electrons, respectively, between atoms. Refer to Figure 2.7 for visual representation. Carbon requires 4 electrons to fulfill the octet rule. This can be achieved through various methods, as illustrated in Figure 2.8. Carbon skeletons form through covalent bonds, creating structures like straight chains, branched chains, or rings. These formations are known as carbon skeletons, with carbon atoms located at the angles where lines meet. Hydrogen atoms often accompany these carbon structures. The carbon skeleton can be arranged in various forms, depicted in progressively simpler figures. Refer to Figure 2.9 for visual representation. Access the text alternative for detailed descriptions of these arrangements. Covalent bonds can be nonpolar or polar. Electronegativity, the relative attraction of each atom for electrons, determines electron sharing. When two atoms of the same element share electrons equally, the bond is nonpolar. Unequal sharing results in a polar covalent bond. Electronegativity increases from left to right across a row, and from bottom to top in a column on the periodic table. Among the 4 most common elements in living organisms, electronegativity ranks from least to greatest as hydrogen, carbon, nitrogen, and oxygen. Electrons carry a negative charge. In a bond, the more electronegative atom gains a partial negative charge, while the less electronegative atom gains a partial positive charge, denoted by delta plus or delta minus. Polar bonds typically form between different atoms, except in carbon-hydrogen bonds. Covalent bonds can be polar or nonpolar. Nonpolar molecules have nonpolar covalent bonds, like OO and CH. Polar molecules, such as water, contain polar covalent bonds like OH. Interestingly, nonpolar molecules can include polar covalent bonds if their partial charges cancel out, as seen in carbon dioxide. Amphipathic molecules have both polar and nonpolar regions. A key example is phospholipids, which play a crucial role in forming cell membranes by aligning their polar heads with water and nonpolar tails away from it. This slide features a figure illustrating nonpolar, polar, and amphipathic molecules. Please refer to the text alternative for detailed descriptions of the slide images. Intermolecular attractions are weak chemical forces between molecules, crucial for the shape of complex structures like DNA and proteins. Hydrogen bonds form between polar molecules, involving a partially positive hydrogen atom and a partially negative atom. While individually weak, these bonds collectively exert significant influence, particularly on water molecule behavior. Hydrogen bonding is a type of intermolecular attraction. It occurs between polar molecules, involving a partially positive hydrogen atom and a partially negative atom. This bond is individually weak, but collectively strong, significantly influencing the behavior of substances like water. Intermolecular attractions include unequal charges in nonpolar molecules, where electrons orbit unevenly, inducing unequal distribution in adjacent atoms. These forces are individually weak, but collectively strong. Hydrophobic interactions occur when nonpolar molecules are in a polar substance, and if within a large molecule, they're termed intramolecular attractions. Molecules are categorized into organic and inorganic types. Organic molecules contain carbon and are associated with living organisms. In contrast, inorganic molecules encompass all others, such as water, salts, acids, and bases.